Quantum mechanics is a theory that you use when you study small systems like atoms. It's a very successful theory, but also very messy and confusing. And not just from the philosophical sense, but also the way it's defined. There's like 6 postulates that are kinda arbitrary and abstract. The holy grail of this theory is the Schrodinger equation. It's one of the first things you learn when you study quantum mechanics. And supposedly, when you solve this equation, you know everything about the system you study. But it's just differential equation. There is nothing quantum mechanical about differential equations, right? But I was always wondering, if this is just a differential equation, then where all that quantum weirdness comes from, like quantization of the energy levels. And solving this equation is usually the most difficult step when you study small systems. But if you want to learn quantum mechanics and there is nothing quantum mechanical about this equation, then why bother and why not solve it numerically? The most quantum mechanical stuff comes after you solve this equation. And therefore, I try to solve it numerically, so that I don't have to deal with this non-quantum mechanical step, since the only thing I care about is quantum mechanics itself, and where all that phenomena come from. But surprisingly, doing this gave me much more intuition and understanding for quantum mechanics than I originally expected. And suddenly it became crystal clear what the quantum mechanics is all about. By the way, do you often use PDF documents? Because if you do, you probably know it's very hard to edit them. But with the use of UPDF, it's not that hard anymore. You can edit the text like a Word document and also move the text around, which is very useful. Because, for example, here I have an old train ticket. And if I change the date, it is suddenly a new train ticket. Just kidding. There is a QR code, so don't do it. Anyway, you can also easily add a picture and link to it. You can annotate the document very easily by highlighting, underlining, crossing. You have a pencil tool. You can also attach a file directly into the document, add stickers, sign the document, and many more. You can also easily organize the pages, and you can run the document as a presentation page by page. After you are done editing the PDF, there are plenty of options how you want to export it. But what is the most exciting thing about all of this is the integrated GPT-4o and DeepSeek R1 AI, where you can have a chat about the PDF. And there are many more features apart from those I have shown to you. And you can get all that for just 1/6 of the price of Adobe. Moreover, you can use the license to up to 4 devices, so you don't have to worry if you have a lot of computers. So, if you are interested, by using the link in the description, you get a very good discount for the UPDF Pro version. Moreover, a UPDF 2.0 is coming out soon, on May 29th. So you can get an early bird pricing of $10 discount. But all existing users of UPDF Pro will also get a free update, so you don't have to worry not being compatible with the 2.0 version. So thank UPDF for sponsoring this video, and now let's continue. Okay, you might be asking, I just let the computer do all the heavy lifting. How can that help me to understand the quantum mechanics better? And that is a fair point, but solving a differential equation numerically is not as straightforward as it might sound. So let me start from the beginning. If you have a system to study like a hydrogen atom, then you have to use quantum mechanics. So you write down the Schrodinger equation, but there is this h there, which is called the Hamiltonian, and it completely defines the system you are working with. It is something that you have to find, otherwise you don't have the equation to solve. And each quantum mechanical system will have its own Hamiltonian. For hydrogen atom it's kinda complicated, and therefore I'm going to study a simpler systems, like finite potential well and harmonic oscillator, which are the most common systems you study at the course of quantum mechanics. And therefore I can simply compare our numerical results with the analytical ones. Let's start with the finite well potential, and once we solve that, transition to harmonic oscillator and even more complicated potentials is kinda straightforward. So if you want to use quantum mechanics for this system, then we have to write down the Schrodinger equation. Then find the Hamiltonian, which is just a sum of kinetic and potential energy. Potential energy is kinda simple. It is just different constant values at different parts of the potential. So classically, a particle with total energy higher than the potential well can move freely from -infinity to infinity, but particle with lower energy is bounded by this potential well. The first quantum mechanical thing you do is that you make an operator from this Hamiltonian, according to the postulates. So you just replace the momentum by momentum operator and position by position operator. And that is the only quantum mechanical thing you do before solving the Schrodinger equation. So far, we used the postulate about the Schrodinger equation and the postulate about operators. And then what you are left with is the full Schrodinger equation for this system that you have to solve. However, it is not necessary to solve the full Schrodinger equation if your Hamiltonian is not time-dependent explicitly, because then you can split the wave function and integrate the time part independently. Therefore, solving this equation is enough. And the time dependence of the solution is then given by multiplying by this complex exponential term. So in the end, this is what we need to solve, which is the second order ordinary differential equation, which is known as stationary Schrodinger equation. And this is the form of the equation you will be solving in most of the quantum mechanical courses. And there we have it, right? Just write it down into the computer and you have figured out everything about the system of finite potential well. When I first tried to do it, I thought it's gonna be this simple. So I started to write down the code and then realized, wait, this is wave function, which is my goal to find. And this is the energy of the particle. But what number should I put in? I know that energy of the particle is quantized, but how is this information contained in the Schrodinger equation? In principle, I can put any number I want here, and it will still be a differential equation that I can solve. So what can I do? Just put a random number there and solve it, and you will see what happens. But there is another problem. Since this is a second-order differential equation, to get a particular solution, you have to specify the initial conditions, which are initial value of the field at particular point and initial derivative. Imagine one of the simplest second-order differential equation, where a second derivative of a function plus the function itself is equal to 0. A solution to such a differential equation would be, for example, a function sine of x. If you make a second derivative, you get minus sine of x, which gives you identity, which is a proof that sine of x is a solution. But this solution is not unique. You can have a sine of x multiplied by arbitrary constant. And you can easily find out that this is also a solution. But this is still not the full general solution. You can also have a combination like this, with two arbitrary constants, and it is also a solution. But if you specify that you want a function that is equal to 0 at x equal to 0 and have a derivative of 1 at x equals 0, then only one particular combination of these constants will satisfy this condition. So if you are trying to solve differential equation for such potential that is symmetrical, then you can expect your solution to be symmetric or anti-symmetric at the center of the potential. Both options are possible, and therefore you have to solve it separately for each. If you're looking for a symmetric solution, then you look for a function that looks like this at the center, and therefore have zero derivative at 0 and some non-zero value which we can choose to be 1. But I will later explain what this choice actually means. For anti-symmetric case, the wave function should look something like this, and therefore have 0 value at 0 and non-zero derivative which we choose again as 1. I will come back to this later, but since now we have initial configuration set, let's solve the Schrodinger equation. So I have created this simple Mathematica document where you find all the theory and all the steps in much more detail than I'm going to show in this video. So if you're interested in playing with this stuff, you can find it on my Buy Me Coffee page. It's for free, so don't worry. Link will be in the description. So again, this is the equation we have to solve with a finite well potential. So we can define some width and height of the potential. I'm going to give it the height of 3 units of energy and the width of 10 units of space. So in Wolfram Mathematica, I define it by the using of these step functions, which are basically 1 if they are positive and 0 if they are negative. And this is how the potential looks like. So it has certain value at energy equals 3, then it's 0 and it's 3 again. And the width is overall 10 units of space. I have to solve this equation. So this is how the equation looks in Wolfram Mathematica. So I have the second derivative of the wave function here. The potential I have defined, the wave function itself, and that's equal to the lambda, which is the energy of the particle, which I don't know yet, and again multiplied by the wave function itself. Since I don't know what the lambda parameter should be, I use this parametric and the solve, which allows me to put a parameter into the differential equation, and then I can move the parameter and observe how the solution changes depending on the energy of the particle. Here you can notice that I used the initial configuration such that the value of the field at the center is equal to 1 and its derivative is equal to 0, which means that I'm looking for the even solution to the wave function. And then I specify what the wave function looks like, what is the symbol for the range, and what is the symbol for the parameter I use. So after I solve it, I can plot the solution, which I did here. This blue area represents the shape of the potential, the red line represents the energy of the particle, but it's also a 0 for the wave function. And this black line represents the shape of the wave function itself. And now I can modify this energy of the particle and observe how the solution changes. And when I first saw this, I couldn't make sense of it. How do I find the correct energy levels? But what I did notice is that none of these solutions actually obey one of the postulates of quantum mechanics. Namely, the first one, which is the postulate about the wave function. The first postulate tells us that all of the informations about the quantum mechanical system is captured entirely by the wave function. So all the informations about the position, energy, and momentum of the particle are captured in this function, in this shape. And there are methods how to extract this information. We are now working with the so-called position representation of the wave function, meaning we have our wave function as a function of position. This represents the probability amplitude of finding the particle at a certain location. And if you want to know the probability density, the only thing you have to do is to square the wave function. This function now shows what is the probability density of finding the particle at a certain location. And you can see that there are some areas where the probability is higher, but there are also areas where the probability is 0, which basically means the quantization of position. But where is the quantization of energy? Also, our solution suggests that the probability of finding the particle beyond this potential barrier goes through the roof, which is completely contradictory result, because if the energy of the particle is lower than the potential barrier, it should actually never be there, and the probability of finding it there should be 0. So this clearly indicates that the wave functions I'm showing you are wrong. But why? Did I mess up something with the numerical solution? If you have a particle somewhere, then the total probability of finding it somewhere must be 100%, right? The total probability of finding the particle in all space equals to taking an integral of this probability density from -infinity to infinity. And this has to be a reasonable finite number, which is chosen to be 1, which is a normalization condition. This doesn't have to be 1. It's just the most convenient number to pick as your 100% probability. But in principle, you can choose any finite number as your representation of 100% certainty. But the number you choose will actually fix the choice of the initial configuration at the center. Because if you remember, we had some freedom in picking this particular number. But if you choose some normalization condition, it will fix this number. This condition is obviously satisfied only by such wave functions that converge to zero at infinity. But anyway, this condition is called the square integrability of the wave function, and it's a part of the first postulate of quantum mechanics. But if you look at R squared solution, you can see that there is no way this condition is satisfied, as the solution strongly diverges behind the boundaries. But then I noticed that some solutions diverge later than others. For example, this one diverges very quickly, but this one diverges very slowly. It almost looks like there is one solution that is fully squared integrable, but the computer hasn't enough precision to actually find it. Maybe we can get closer by hand. So we have 105 here. So if I put 1, it's 9, 4, 5, 4, 3, 4, 5, 1, 3, 9, 8, 3, 7, 6, 5, 7, 5, 1, 9, 8, 9. So you can see that by doing this, I can slowly get to a function that is squared integrable. So maybe only such energies for which the wave function is square integrable are the only energies the particle can have. And this is the quantization of energy. If I remove the square, then you can see that the solution is going up and down from the negative values to positive values, right? And therefore, clearly there has to be a value for which these tails of the function are exactly at zero. So there must be a solution that is squared integrable. And that is the wave function that is physical, and everything in between is unphysical. So the information about the quantization is not hidden in the Schrodinger equation itself. It's hidden on the conditions that are imposed on the wave function itself, namely the square integrability. So you can say that the quantization of energy is a direct consequence of the square integrability condition. So if you want to find the energy levels of your system by solving it numerically, then all you have to do is just move this handle and observe when this solution jumps from negative values to positive values. Because somewhere in between there is the value for the energy where this wave function is exactly asymptotically at zero. And by this you get approximate energy levels. So there is one at a value around 0.05, another one here, another one around here, another one around here, and so on. So you get the point. If you solve the Schrodinger equation analytically for this system, you would find out that the wave function in these areas generally looks like this, where you have two exponential terms. One part always diverges as x goes to minus infinity on the left or plus infinity on the right. And here your teacher will usually claim that the constants in front of the divergent parts of the solution to be zero. And you see that the divergence goes exponentially with x and only linearly with a constant in front of it. And therefore it's a very sensitive result. And there is no way you could find a numerical solution that would converge on a reasonably large position interval, unless the constant is exactly zero. And I didn't quite appreciate at the time that this step largely restricts the possible energies the particle can have, since then you also have to continuously fit it on the wave function inside the well. And only solutions of certain energies are good enough. Otherwise you cannot do this fit. This was always kinda messy part for me. But when I solved it numerically and realized that it's just this condition that is responsible for the quantization of energy levels, it suddenly clicked all together. I feel like I finally understood what the quantum mechanics is all about. You just find the Hamiltonian of the system you are working on, replace the observables by operators, solve the Schrodinger equation, which gives you in general a bunch of unphysical solutions, and therefore pick only such solutions that satisfy this square integrability condition. Those energies you had to pick are the only possible energies this system can have, because other energies would give you unphysical wave function. Simple enough, isn't it? But what is also interesting is what happens if I go with the energy of the particle above the barrier. And here you can see that the wave function suddenly becomes periodic. Therefore, it doesn't blow up behind the barrier. And therefore, all energies of the particle are suddenly allowed. And particle can be anywhere in space. Therefore, it's dislocalized. You can also notice that the wavelength of the particle is shorter inside the well because it has a larger kinetic energy, and it's longer behind the barrier. We can also look at the odd solution. And the differential equation is completely the same, but the only thing that has changed is the initial configuration. So here the value of the field at the center is now 0. As you can see, this is a typical odd function. So it has a 0 value at the center, and the derivative is equal to 1, but it can be any other number. It's just how you define this normalization condition. So when I do this, and I plot the wave function, and I change the energy, you see that it's different. But I have a better picture, I believe, here. So again, it's completely the same thing, but you can find the different energy levels of the systems that are also allowed, that you couldn't find when you are looking for these even solutions. So here you can see that there is also this energy allowed, and also this energy allowed, and so on. And again, if you go above the energy of the barrier, you will see that the wave function is suddenly periodic. If you wanna solve it for some other potentials, then one most commonly used is the harmonic oscillator, and I also did that, which I have here. And the good thing about harmonic oscillator is that its energy levels are very nice numbers, so we can nicely compare it with the analytical solution. Here I choose all the constant to be 1. So here I have defined the potential, which is very simple, it's just a quadratic well. Here is the Schrodinger equation, and again it's completely the same, only thing that changed is this potential. Here I choose initial configuration to be 1 for the value of the field at 0 and the derivative to be 0, which means again that I'm looking for the even solution to the wave function. And here I have the plot for the wave function for the harmonic oscillator. And we can basically now look whether the energy levels correspond to this numerical solution. So when I go around 0.5, I see that they are almost square integrable. You can see that they are kind of going off at the edges, so it's not exact. But when you go further, 1.5, there is nothing, because we are only looking for the even solution, and the first one is odd solution. So we can only find the second one, so at 2.5. Maybe I can put it by hand, and you can see that it's very close to being square integrable. And you can go on, for example, 4, 6, and so on. I can go maybe 10. And let's go like this. For odd solution, I have also here, and I have changed this initial configuration. Again, the value of the field as a setter to be 0 and its derivative to be equal to 5. Here I choose 5 because if you choose 1, then the wave function is very small. You can see that you cannot see much, but the energy levels are completely the same. You can for example write 1.5 here, and you get correct energy level. And if I put here 5, for example, the only thing that changes is the scale of the wave function. So when I do it, you see that it's just scaled up. But when I put the correct energy level here, I get the correct wave function. So you can see that numerical analysis is not just crunching the numbers, or at least for me it's not. It gave me an intuition and understanding for quantum mechanics that I don't think I would ever get by just reading scripts or books. It's always worth it to see the same thing from different angle. So if you have Wolfram Mathematica installed and you want this document, again, it's free to download on my Buy Me Coffee page. So I will provide the link in the description. So if you are interested, click on it and play. You can find a lot more details there. Also the analytical solution and how it all fit together. But please forgive my English there because I was really typing it fast and I didn't give it much of a time. Thank you for watching, and I also thank all of you who support me on Patreon or any other way. I largely appreciate it, and it really helps me to create these videos. Thank you, and I see you next time.